Hello, physics students. Okay, so I'm going to go quickly through the review sheet. I'm kind of moving really quick because it's long and I don't feel like spending hours uploading this thing. So I want to make a video that's pretty quick. So I'm going to go through them. I'm going to show how to do the examples, but I might not spend super long explaining everything. So just keep that in mind. This is very close to the test. I'm basically giving you the test, but I'm changing the numbers. You really want to know that? Okay. Uh, Test will be multiple choice on Castle Learning. You know the drill. Okay, so now to get through this, let's go. The do now starts with probably the hardest as far as time-consuming problem. What is the magnetic charge? What is the magnitude of the electrostatic force between two electrons when they are 0.25 meters apart? Okay, so electrostatic force is kind of like force of gravity. It reminds me of that, especially because it's got the inverse square distance between the two centers, just like gravity. You got a constant up here, like the gravitational constant. Instead of mass, you have charge. Okay, so my K in the reference table, 8.99 times 10 to the 9. My charge on one electron, well, they're two electrons, right? So they have the exact same charge. So it's 1.6 times 10 to the negative 19 for one, and then 1.6 times 10 to the negative 19 on the other. Okay, kind of long, but that's okay. On the bottom, they are 0.25 squared. Now, how I like to do all this work is I like to look at it like this. I like to do 8.99, especially if I'm not using a calculator, times 1.6 times 1.6. I'll do all the numbers out front, and then I'll do 10 to the 9 times 10 to the negative 19 times 10 to the negative 19. I probably do this because I'm an algebra teacher, because then I have my exponent rules here. Here I just do 8.99 times 1.6 times 1.6. Sorry, let me turn this light on so you can see my calculator just a little bit better. Okay, hit enter. I get 23 on the top. I get 23.0144. Here I just do times 10. 9 minus 19 is negative 10, negative 29. Now I'm going to probably want to move it over. So it's 2.3 times 10 to the negative 30. If you have the graphing calculator, remember, you can just do it this way. You can put the whole messy number here. I'm taking a lot of time. Second E 9 times 1.6 second E negative 19 times 1.6. Hope I'm doing this right, or maybe I should be putting these in. Oh, negative 28 because I'm moving it to the left. Sorry, 28. 2.3 times 28. Just different way of doing it. Okay, this is the right answer. So I have on top, the top number here is 2.3 times 10 to the negative 28. I still haven't done the bottom yet, but that's pretty simple. 0.25 squared is 0.0625. So I'm just going to do 2.3 second E, let me make that, 2.3 second to the negative 28, and then divide that all by 0.0625. And my final answer is 3.68 times 10 to the negative 27, which is a tiny number, newtons. Okay, remember this is in newtons. Okay. I think that's the most work you have to do, okay? That problem. So look that over. Be careful with that one. Okay, skip over the objective. Which diagram represents an electric field? The question is, when you're looking at an electric field, the electric field lines represent how a positive charge would behave. Not a negative, it's always a positive. How would a positive charge behave? So which one is correct? Well, if I put a positive charge here next to a negative charge, it would be attracted inwards. It wouldn't want to go that way, but these arrows are pointing out, not that. Now, if I put a positive charge here against another positive charge, they would repel. They would push each other away, but these arrows are pointing in like they'd be attractive, so it's not that. I'm down to these. These two electric charge plates. One's positive on top, one's negative on the bottom. Which is the proper way a positive charge would behave? Here, a positive charge would want to go towards the negative side and away from the positive. It would behave in this direction, like these arrows are pointing. It would not be attracted to another positive plate. It would be repelled by the positive plate. Keep that in mind. So whenever you're looking at electric field arrows, what direction are they going? Ask yourself, how would a positive charge behave? Okay, next one. Oh, see, they're moving. What's the difference between electrostatic and gravitational forces between two objects? Pretty straightforward. Electricity, or electromagnetism, or electrostatics, electromagnetism, can both be attractive and repulsive. Gravity is really one direction. It's only attractive. Hey, if you could ever make it negative, you'd win repulsive, you could probably win the Nobel Peace Prize. A Nobel Prize in Science. Okay, so, next one. How would electromagnetic force act on both a proton and electron at point P? This is kind of the opposite of 2 questions ago. So if I put a positive charge here, well, a positive charge would want to get away from the positive plate and be attracted to the negative plate. So it would go in the downward direction. It would go down. If I put a negative charge between these 2 plates, well, it'd be attracted to the positive and want to get away from the negative plate. So that's basically it. Pretty straightforward. Remember, opposites attract, likes repel. So that brings us to this one. Now I look at this one, I say, well, what are the charge in points A and B? I think this was one of our do nows, or exit tickets. Well, first of all, they're repelling each other. Okay? So they have to be like charges. There is no doubt in my mind these are like charges because there's no attraction between them. This is empty space. The force between the 2 of them is 0. They're pushing each other away. They're going, get away from me, get away from me. Now, okay, so I know they're both the same. So whatever A is B is, or whatever B is A is. So my next question is, we'll go back to the other question. Like, how would a positive charge behave? Well, a positive charge would be attracted to a negative charge. So this tells me a positive charge here is attracted. So this must be a negative charge. And we already said they're like charges, so this would be a negative charge. So you got 2 negative charges. Okay. This is back to this one here. The big daddy problem. But it's not as bad. You don't have to figure it out. Okay. It says an electrical force of 16 times 10 to the negative 8 newtons exists between the point charges Q1 and Q2. If the distance between these 2 charges is quadrupled, the new electrical force between these 2 charges would be. So, if I look at this, this is my charge. And whatever this is, whatever K, Q1, Q2, over R squared is, it's equal to 116 times 10 to the negative 8. Okay? But I'm changing everything. I'm going to say, well, that's not going to, K is a constant. The two charges are going to remain the same, Q1, Q2. So you keep the same charges. So far, they look exactly alike. The difference is the distance is quadrupled. So 4r squared. Now if I do this new force is going to be K, Q1, Q2. 4 squared is 16 r squared. So this is really, I'm bringing this down here, K, Q1, Q2 over r squared. It's 1/16 of that. But I have this number already. This number is 16 times 10 to the negative 8. So I have 1 over 16 times 16 times 10. Oh man, to the negative 8. I made this way too easy. 16 divided by 16 is just 1. So the new force equals 1 times 10 to the negative 8 newtons. Ooh, interesting. Interesting. I made it too easy. Okay, it says here. It says in the diagram below, conducting sphere A has a charge of 12 times 10 to the negative 6 coulombs, and this one has a charge of 10 to the negative 10 times 10, 8 times 10 to the negative 6. Now this is all about distribution of charges. Remember, charges always want to balance out. Okay, so when you bring these together and they touch, electrons are going to flow from the one with the, let's say it's positive or negative. But the charges are going to balance out. 8 and 12. How do you figure this out? Well, it's really easy. 12 plus 8 equals 20. I'm going to leave these numbers out because they have the same exponents. Okay, it's the same thing on both of them. 12 plus 8 is 20. 20 divided by 2 is just 10. So the final answer is 10 times 10 times 10 to the negative 6 on both of them. On both of them, not just this one. They're both the same. So they're evenly split. They're both the same. So the charge on sphere A is the same as charge on sphere B. So either way, they're going to be 10 times 10 to the negative 6 coulombs. Okay. Okay, this is a little bit interesting one. The one on the test is going to be a little bit more, let's say, it's a multiple choice with a multiple numbers of these different patterns. Okay, so it says for the conducting spheres where sphere A has a net positive charge. So that means there's mostly positive charges here. Now here, sphere B is neutral. That means it's got some positives, it's got negatives, okay? What is the charge distribution on sphere? What does it look like? How is it balanced out? So here I would have positives all around. What would happen over here, though, is as I brought this closer, any positive charges here would be, what would happen, is when you brought this closer, the electrons in sphere B would start being attracted over towards sphere A. They want to go there. Like, hey, we want to get over there. There's a nice positive charge. On this side, remember, the protons don't move. They would just all stay there by themselves. So it kind of would look like that, where the electrons would be moving to get to close to this positively charged sphere, and the protons would just stay there and say, leave us alone. Okay? Okay. Here's one. Guys, we're going to definitely use the reference table for this. So I gave you a reference table on this and on the quiz. This formula for resistance is pretty simple. Resistance on a wire is just. This is just a number. This is determined in a lab. You might have to find it out yourself, but that's just a number. It's called resistivity of a particular metal. There is on page 4 of the reference table, it says the resistivity of all these materials at 20 degrees Celsius. So whenever you see that on a question, they want you to go there and get that number. It's going to be a different one than copper. I am using copper in this example. And the resistivity of copper, our rho, is 1.72 times 10 to the negative 8. That's just from the reference table. Then I got to do the length. Well, the length is, from this question, 10 meters. And the cross-sectional area, or A, is 2.0 times 10 to the negative 2. Now, all of you probably already know cross-sectional area, but just to be a quick refresher, it's how thick the wire is. So you measure this area here of that. If you cut the wire and you had a little circle there, that would be what they call the cross-sectional area. So it's saying how thick or wide, is this wire. Now, if you notice, that area is on the bottom. So that means as a wire gets thicker, right, this number becomes bigger, the resistance becomes less. Electrons can flow better through it. If it becomes narrow, this number becomes smaller, the resistance becomes higher, and it's harder for electrons to flow between them. This also says the length of the wire. The longer the wire, the more resistance there is. And this is just dependent on the material that the wire is made out of. So I'm going to put this number in my calculator, 1.72 times 10 to the negative 8 times 10, my length, all over my area, 2.0 times 10 to the negative 2. 20 degrees Celsius. Remember, as temperature changes, resistance changes, but 20 degrees Celsius is room temperature, I guess, or standard temperature that they measure this at, 20 degrees. So I'm going to put this in real quick, 1.72 times 10 to the negative 8 times that by 10. I get that number, 1.72 times 10 to the negative 7. I'm going to divide it. Of course, why wouldn't that be? I should have thought that right away. Divided by 2.0, or 2, to make things harder on myself, e to the negative 2. And I get this number, 8.6 times 10 to the negative 6 ohms. That's the resistance for that copper wire. Remember, resistance is always in ohms. I guess you can spell out ohms, or you can do the omega symbol. That's another way to write ohms. Pretty straightforward formula. Remember this one. Remember, when you see this, you got to look in the reference table. Reference table. Get it. All right, let's move on. Which diagram represents the electric field between two oppositely charged conducting spheres? Positive, negative, positive, negative, positive, negative. Negative is always attracted to positive. So negative wants to go to positive. Negative wants to go this way. Now a positive, if it was around here, it want to push away other negatives. So I look at this one. Okay. Let's look at this one. So a positive would be attracted here and be repelled over here. That makes sense. Here it says a positive would be repelled and attracted here. That wouldn't be true. Here it says a positive would be attracted and a positive would be attracted. That's not true. Here it says a positive would be repelled. That's correct, but a positive would not be repelled with a negative. Only possibility is this one, number 2. Positive repels a positive, negative attracts a positive. So the idea here always is, how would a positive charge behave in those situations? Just imagine putting a proton there. This one looks a lot harder than it really is. What you do here is, we know that the charge on an electron is 1.6 times 10 to the negative 19. I wish we could talk more about this. I love this idea. Is that charge is quantized, which means a charge is a little piece of something. It's a unit. It's one. Like this is one pen cap. Okay, you could have 2 pen caps. You could have 1, 2 pen caps. You could have 3 pen caps. You cannot have 2.5 pen caps. So every time an electron is taken away or added, you have just another one. Okay, so you take that way. So it's either 1 or 2 or 3 electrons. And each one of those is worth 1.6 times 10 to the negative 19. There's no other, that's the only charge an electron has on it. There's no such thing as another charge. So all of these numbers have to be whole number multiples of 1.6 times 10 to the negative 19. Well, what I see here is that they all have 10 to the negative 19, so I'm going to ignore that on all of them. I'm going to just look at these numbers. I'm going to ask myself, okay, hopefully we all see this, which is a whole number multiple of 1.6? 2.3 divided by 1.6? Nope. 3.2 divided by 1.6. 2. That's our answer. This is the only possible real situation that can occur. If I do the other ones, 4.1, you'll see I'll get a decimal divided by 1.6, right? Or 6.0 decimal. So they have to be real number multiples of whole number multiples of 1.6. That's the only way. So you can have 3.2, 1.6 times 3, another one, let's see, 4.8. I'm sure Peter right now is just doing them in his head. He's rattling them off. 1.6 times 4, 6.4. 1.6 times 5. I'm getting out of control here. 8. Oh, you can get nice even 8. So, and so on and so forth. But they all have to be whole number multiples of 1.6 coulombs. Okay. Next one. All right, I'm sorry, we're almost done here. 22 minutes in. You almost get a full lesson out of this. It says moving 10 coulombs of charge with a conductor requires 75 joules of energy. What is the potential difference needed to accomplish this? V equals work over charge. Okay, I got to find V, so this works out good for me. So I have 75 joules. Work has to be in joules over 10 coulombs. 75 divided by 10. Potential difference, 7.5 volts. Very quick, very quick. This is kind of going back to the resistance one. Oh man, I'm so slow. Okay, which change would decrease the resistance of a piece of wire? Well, if you looked at the formula, remember, this doesn't change. This is whatever the wire is, right? L over A. So increasing the wire's length would increase the resistance. Okay, so I want to decrease. Increasing the wire's resistivity, this number, changing the material, but increasing. Decreasing the wire's temperature, or decreasing the wire's cross. So if you make this number smaller, this resistivity gets bigger. Decreasing the wire's temperature. As temperature goes up, resistivity goes down. Okay? And as temperature goes down, resistivity goes up. So in a sense, that's why we have fans on our computers, to keep all the components cool, so that the wires and the internal structure of the computer, the connections to the circuits, all have lower resistance and stay cooler. And it can move faster and don't get as hot. Electroscope is a device with a metal knob, metal stem, and freely hanging metal leaves used to detect charges. The diagram below is a positively charged electroscope as a positively charged glass rod. So I'm bringing a rod close by here, and it's positively charged. Were the brought near the scope, what would happen to the separation of the leaves? Well, what happened is, this is mostly positively charged, and this is negative, and they separate. What happens if I bring this positive more electrons? This is a positively charged. So at this point, if any electrons were left, they'd be pushed down here. And these leaves would come closer together. That was a tricky question. So these leaves would actually become closer together. Because what happens is the electrons, oh wait, no. I'm sorry. Yeah, the electrons would flow down, and these leaves would get further apart. They would go more towards here if there was any remaining, so. But then the net positive. I'm going to say stop. I'm going to talk about this real quick. Negative charge, whatever negative is left. There's got to be some electrons, so this is not completely positively charged. These leaves would become less positive as the electrons ran away. And they ran down these two paths. This charge, where it's both positive, would suddenly start becoming a little bit more negative or less positive, if you want to think of it that way. And the force of repulsion between these would go down because it'd be closer to neutral. And finally, exit ticket. Okay, can I do this in under 30 minutes? A positively charged rod is held near the knob of a neutral electroscope. Which diagram represents the distribution of charge in the electroscope? Here's the better version of that question. Here, you go like this, boom. You bring something positive. Electrons are attracted. Electrons want to get here. They want to get to the top. They want to make friends with that positive rod. So any spot you have where you bring a positive charge, electrons rush there. Now, it says it was a neutral electroscope. So when it was first here, before anything was here, there was electrons and protons all together living in harmony inside this device, the electroscope. There's positive, negatives, there's positives here, negatives there, positives here, negatives. They were all mixed up. Now what happens is I bring the positive charge by, and suddenly the electrons want to be friends with this. So the top of the knob definitely in all of these looks like that. Now what happens, though, is, remember, protons don't move. So while these go up here to be attracted to those extra protons, the electrons move up. They leave the protons by themselves. So what happens is you have a positive charge on these leaves because the electrons have all moved to the the suburbs of the knob here and become better friends with that. So this doesn't work because whereas all the protons, they would have to stay behind. The electrons would all want to go there. This doesn't work because where's the electrons? This wouldn't work because it would indicate that the electrons don't want to be near the positive charge rod, but they do. They want to get there. So what in a sense is happening is the electrons want to go there, and they leave the poor protons because protons cannot move. Okay? Only electrons can. Remember, that's an important rule. All right, guys, I'm stopping it here. 2 minutes short of 30 minutes.